Picture the heart of ancient Rome, engulfed in a raging inferno. Flames leap from building to building, devouring wood and cloth, turning entire neighborhoods into ash and smoke. This was a terrifying reality for Romans, where fire could erase generations of work in a single night. Yet amid the chaos and destruction, something remarkable stood: firm structures with roofs that refused to burn, as if protected by some kind of ancient magic. How did they do it? How could a civilization 2,000 years ago create roofs capable of withstanding the very fires that regularly brought cities to their knees? This is the incredible mystery we're about to explore: the hidden genius of Roman fireproof roofing. The Romans didn't just build, they engineered for eternity. Their solutions weren't born out of luck or superstition, but from brilliant observation, relentless experimentation, and a deep understanding of materials that even today leaves experts in awe. Imagine a roof so resilient that centuries later, after empires have risen and fallen, it still stands strong against time and the elements. These roofs weren't just practical. They were a testament to human ingenuity in an age without modern tools or science as we know it. They tackled one of humanity's oldest and most devastating problems with creativity and grit, and in doing so, they left behind clues that continue to captivate historians, architects, and curious minds like you and me. Join me as we step back into the world of ancient Rome, not as distant observers, but as detectives unraveling one of history's most fascinating engineering puzzles. We'll uncover the secrets behind their fire-defying designs, the materials they used that seem almost mythical in their effectiveness, and the brilliant minds who turned catastrophe into opportunity. This isn't just a story about it's about how human ambition and imagination can conquer even the most overwhelming challenges. And by the end of this journey, you'll see the ancient world in a whole new light, filled with wonders waiting to be rediscovered. In the year 64, a catastrophe struck that would sear itself into the memory of the Roman world. A fire began in the shops around the Circus Maximus, and fueled by strong winds and tightly packed wooden buildings, it exploded into an unstoppable force. For 6 days and 7 nights, the flames raged, leaping across narrow alleys and consuming entire districts. When it was finally contained, then reignited and burned for another 3 days, the scale of the devastation was almost unimaginable. Of Rome's 14 districts, only 4 remained completely untouched. 3 were leveled to the ground, nothing but ash and smoldering ruin, while the other 7 suffered massive damage. Countless homes, temples, and public buildings were lost. The human cost was immense, leaving thousands homeless and destitute. This was the Great Fire of Rome, a pivotal moment that exposed the terrifying vulnerability of an entire city built from wood and carelessness. The event was so traumatic that it forced a fundamental and immediate reckoning. For the first time, the very fabric of the city was seen as the problem. The common building materials, wood for beams, frames, and roofs, and flammable straw and reeds for thatching, were now understood as a collective death trap. This disaster created an urgent city-wide demand for change. It was no longer enough to have bucket brigades and vigilante fire watchmen. The solution had to be architectural. The fire created a powerful political and social imperative for Emperor Nero, who, despite the infamous myths, actually initiated ambitious new building codes in its aftermath. These regulations mandated wider streets to act as fire breaks, and most crucially, encouraged the use of fire-resistant materials for construction, particularly for roofs, which were the most vulnerable point for spreading embers. This catastrophe became the catalyst for one of history's most significant bursts of architectural innovation. The Romans were brilliant practical engineers, and they already possessed knowledge of materials that could withstand immense heat. The fire provided the desperate necessity to apply that knowledge on a massive urban scale. It shifted the entire philosophy of building from simply creating shelter to engineering for survival and permanence. The quest was no longer just about building beautifully, but about building smartly and safely for the future. This moment of profound loss ignited a revolution in Roman construction, setting the stage for the ingenious and durable solutions we are about to uncover. To understand the revolutionary nature of their solution, we first need to appreciate what the Romans were working with before the great fires forced their hand. The standard roof in a Roman city, especially for the average citizen, was a disaster waiting to happen. The primary framework was almost always wood. Massive wooden beams, known as trabes, formed the skeleton of the roof, supporting a network of smaller wooden rafters and laths. This created a vast, interconnected fuel source hidden just above everyone's heads. Imagine a city block where every attic is essentially a carefully arranged pile of kindling, just waiting for a single spark to set it all ablaze. On top of this wooden framework, the most common covering was terracotta tiles. Now, you might think, terracotta is fired clay, that's not flammable, and you'd be right. An individual tile is not, but the critical weakness was in how they were installed. The Romans used two main types of tiles, the flat, rectangular tegulae and the curved, cover tile imbrices. These tiles were laid on top of that wooden latticework. They were heavy, and they were not mortared or sealed together with any kind of fire-resistant material. Gaps were inevitable, and that was the fatal flaw. When a fire broke out in a neighboring building, it wouldn't be the direct flames that doomed the tile roof first. It would be the embers, burning fragments, carried by the wind, would find their way through those small gaps between the tiles. Once inside, they would land on the dry, dusty wooden structure underneath. A single glowing ember could smolder unnoticed, slowly eating away at a beam until the entire support system was critically weakened. The heavy tiles would then collapse inward, creating a massive breach that allowed oxygen to surge in and flames to roar upward, turning the entire building into an inferno and launching a new storm of embers to attack the next structure. The very thing meant to protect the building, the tile roof, became a trapdoor for disaster. In poorer, more densely packed neighborhoods, the situation was even more dire. Thatch, dried reeds, straw, or grass was a common roofing material because it was cheap, readily available, and provided good insulation, but it was essentially tinder. A thatched roof could be set alight by a stray firework, a cooking spark, or even the intense heat radiating from a nearby blaze. It would ignite instantly and burn with a fierce, rapid intensity, making it impossible to save any home it covered and guaranteeing the fire would spread to anything adjacent. These vulnerabilities created a perfect storm in a crowded urban environment like Rome. Buildings were packed tightly together, sharing walls and overlooking narrow, shadowy streets. A fire starting in a baker's oven in one district could, within hours, leap across entire neighborhoods because every rooftop was a connected highway for disaster. The common materials weren't just weak. They were actively complicit in the city's destruction, turning individual accidents into city-wide catastrophes. This glaring weakness set the stage for a building revolution, one that would address not just the covering, but the very bones of the roof itself. Yet the Romans were not starting from scratch. blindly hoping for a miracle material. Their genius lay in a powerful combination of keen observation and a willingness to learn from the very landscape that threatened them. Just south of Rome, in the fertile, geologically volatile region of Campania, lay the answer. The city of Pozzuoli and the surrounding Phlegrean fields, which translates to the burning fields, was a starkly different world from the 7 hills of Rome. This was a land dominated by volcanoes, where the earth itself smoldered and steam rose from fissures in the ground. It was here that Roman engineers and builders made a series of crucial observations that would change construction forever. They noticed that the local soil had unique properties. After periods of rain, this particular earthy material, a fine, reddish sand, didn't just turn to mud. It underwent a remarkable transformation. It would set into an incredibly hard, stone-like mass. Even more intriguing was its behavior around heat. In areas near volcanic vents, where temperatures were intense enough to scorch ordinary earth into brittle ceramic, this material seemed utterly unfazed. It didn't crack, crumble, or show any signs of weakening. The locals had likely been using it for simple tasks for generations, but Roman engineers saw its potential for something far grander. This material was pulvis pudiolinus, the powder from Puteoli, the Roman name for Pozzuoli. We know it today as pozzolana. What made pozzolana so special was its chemical nature. It was a volcanic ash, rich in silica and alumina, the same essential components of glass. When this fine powder was mixed with water and lime, a common material the Romans already made by burning limestone, a silent, incredibly powerful chemical reaction began. It wasn't just drying out, it was forming a new, stable mineral structure. This reaction, a process we now call a pozzolanic reaction, created interlocking crystals that bound everything together with a grip stronger than most natural stones. The result was a mortar that was not only incredibly strong and durable, but also, critically, completely resistant to water and, most importantly for our story, impervious to extreme heat. It was a concrete that could literally laugh in the face of fire. This discovery was a monumental leap. It moved building technology from the purely mechanical stacking heavy stones or baking clay tiles into the realm of chemistry. The Romans had unlocked the secret to creating an artificial rock that was tougher, more versatile, and more resilient than anything nature provided on its own. They found a way to harness the destructive, primal power of volcanoes and turn it into the ultimate tool of construction, a material that would allow them to build not just for their lifetime, but for millennia. But what made this volcanic ash so special? The secret wasn't in its appearance, but in its hidden chemical potential. Pozzolana is a fine, gritty sand composed primarily of silica and alumina, minerals that are also the fundamental building blocks of glass. On its own, it's just dust. The magic happens when this volcanic powder meets 2 other ancient and common ingredients, lime and water. The Romans produced lime by burning limestone in kilns, a process they had mastered for centuries. When they mixed this slaked lime with pozzolana and water, an incredible, silent reaction began, a process we now call a pozzolanic reaction. This wasn't a simple drying process like mud. It was a complex chemical transformation. The mixture began to form new, incredibly strong calcium silicate hydrate crystals. These crystals interlock and grow over time, even underwater, creating a monolithic, rock-hard mass that is vastly stronger than the sum of its parts. This is the heart of Roman concrete, a material so durable that it has survived 2,000 years of seawater pounding at harbor walls. For fireproofing, this chemical process was nothing short of a miracle. Ordinary materials fail in fire for a few key reasons. Wood, of course, burns. Stone, like limestone, can crack and spall when heated intensely because the minerals within expand at different rates, and the moisture trapped inside turns to steam, exploding from within. But pozzolanic concrete behaves entirely differently. Its complex, crystalline structure is inherently more resistant to thermal shock. More importantly, as it sets, it chemically incorporates water into its mineral structure. This means that under extreme heat, there is no free water to explosively turn to steam. Instead of shattering, the concrete acts as a formidable insulating barrier. It absorbs immense amounts of heat without transferring it to the vulnerable wooden structure underneath, effectively creating a protective shield that could withstand the blistering temperatures of a city-wide fire. The sourcing of this material was also a feat of Roman logistics and ambition. The highest quality pozzolana came from specific volcanic deposits around the Bay of Naples, particularly near the city of Puteoli, which gave the material its name. This wasn't a local resource for Rome. It was a long-distance import. The Romans established massive shipping operations to move this volcanic sand from the south up the coast to Ostia, the port of Rome. Think of the scale: countless ships, their hulls filled with this reddish-brown powder, formed a continuous supply chain dedicated entirely to making construction better and safer. This wasn't just a building material. It was a strategic commodity, so vital to the empire's infrastructure that its sources were well documented and heavily exploited. They even identified and used different grades of pozzolana, with the best, finest-grained ash being reserved for the most critical architectural elements, like the fireproof roofs that would protect their greatest buildings from annihilation. This commitment to sourcing the very best, regardless of distance, underscores how seriously they took the engineering challenge of fireproofing. Now, this chemical process was revolutionary because it created what's known as a hydraulic cement, a material that doesn't just harden by drying out but actually cures through a chemical reaction that can even happen underwater. That's why the Romans could build those incredible harbors, like the one at Caesarea, by pouring concrete directly into the sea. The water didn't stop the reaction, it actually helped it along. This same property is what made it so incredibly fireproof. When a firestorm swept through a city, a roof made with pozzolanic concrete wasn't just sitting there passively. Its very chemistry was actively working against the heat. To understand why, let's compare it to a modern concrete roof for a moment. A lot of modern concrete uses Portland cement, which is fantastic for strength but has a hidden weakness in a fire. It contains a lot of water trapped within its structure. When that concrete is exposed to intense, sudden heat, like from a raging blaze, that water turns to steam in an instant. The pressure from that expanding steam has nowhere to go, so it builds up until it literally explodes from the inside, causing the concrete to crack, spall, and violently break apart. This is called spalling, and it's a major reason why modern structures can fail so catastrophically in fires, exposing the steel reinforcements underneath which then soften and collapse. Roman concrete behaved in the exact opposite way. The pozzolanic reaction creates a much denser, more complex crystalline network that chemically binds water into its new mineral forms. There's very little free water left to turn into destructive steam. When faced with the inferno of a Roman urban fire, this concrete would not explode. Instead, it would act as a massive heat sink, slowly absorbing that incredible thermal energy. It would protect the wooden framework underneath not by being invincible, but by being an incredible insulator, slowing the transfer of heat so drastically that the temperature on the protected side could remain low enough to prevent the wood from even reaching its kindling point. It was a shield, not just a slab. Furthermore, the materials themselves, the volcanic ash and the lime, were already products of extreme heat. The lime was made by firing limestone in kilns, and the pozzolana was literally born from the furnace of a volcano. They had already been tempered by fire, so they weren't scared of it. This ancient recipe created a material that wasn't just strong. It was inherently resilient to the very disaster it was designed to stop. So how did this incredible knowledge spread across a vast empire and survive for millennia? While the Romans were masterful practical engineers, they were not always meticulous documenters of their own processes. Their genius often lived in the hands of the builders and architects, passed down through apprenticeships. This makes the survival of one particular text nothing short of a miracle, a direct line to the Roman mind. That line is a man named Marcus Vitruvius Pollio. Vitruvius was not just an architect. He was a polymath, a military engineer who served under Julius Caesar, and a scholar who possessed a deep desire to preserve the entire body of architectural knowledge for future generations. Sometime around the year 15 BCE, he dedicated his 10-volume treatise De Architectura, on architecture, to Emperor Augustus. This single work is our most comprehensive window into the Roman world of building, and it is within these pages that we find the explicit, detailed instructions for creating the fireproof roofs we've been exploring. Vitruvius didn't just vaguely suggest using volcanic ash. He provided a precise, almost scientific recipe. In Book 2, he dedicates entire chapters to the properties of various sands and mortars. He explicitly names the best sources, stating that the ash from the Bay of Naples, from around Puteoli and Mount Vesuvius, produces the strongest concrete. He details the exact process of quarrying the pozzolana, mixing it with lime in specific proportions, and even the importance of using the right type of water. His writing moves beyond mere instruction into the realm of principle, explaining why these materials work together. He describes the chemical reaction we now call the pozzolanic reaction, observing that when mixed, these materials, on coming into contact with the waves of the sea and being embedded, become a single stone mass, impregnable to the waves and every day stronger. This is a man not just describing a recipe, but articulating a fundamental chemical truth that science would only fully understand 2 years later. His documentation was crucial because it standardized these advanced techniques across the entire Roman world. An engineer in Roman Britain or North Africa might never have seen a volcano, but thanks to Vitruvius, they knew to request shipments of this special sand and exactly how to use it for critical structures. His work became the foundational textbook for Roman engineering, ensuring that the hard-won lessons from disasters like the Great Fire of Rome were not lost, but were instead codified into the very principles of imperial construction. He provided the intellectual framework that turned local experimentation into a repeatable, empire-wide science. Without his meticulous documentation, this knowledge might have remained a trade secret of a few Campanian builders, lost to history instead of becoming a cornerstone of Roman architectural dominance. Vitruvius's influence stretches far beyond the fall of Rome. His manuscripts were painstakingly copied by monks throughout the Middle Ages, preserving this ancient knowledge through centuries where such advanced building techniques were largely forgotten. When the Renaissance dawned, architects like Leon Battista Alberti rediscovered De Architectura, and it became a Bible for figures like Brunelleschi, who used its principles to engineer the magnificent dome of the Florence Cathedral. Even Leonardo da Vinci's famous Vitruvian Man is a direct homage to Vitruvius's writings on the proportions of the human body. The survival of his work means that the Roman approach to problem-solving rooted in observation, material science, and a relentless pursuit of durability was reborn and helped fuel the architectural revolution of the Renaissance, creating a legacy that truly spans millennia. Perhaps the most breathtaking testament to Roman concrete mastery, a structure that perfectly embodies their triumph over fire, isn't a humble roof but a soaring celestial ceiling, the magnificent dome of the Pantheon. This building is far more than a temple. It is a monumental case study in fireproof engineering on a scale that is still difficult to comprehend. Constructed under Emperor Hadrian around 126 AD, its dome remains the largest unreinforced concrete dome in the entire world, a record held for nearly 2,000 years. But its true genius isn't just its size, it's in its survival. The Pantheon has witnessed countless urban fires that have swept through Rome over the centuries, yet its vast canopy has never once been breached by flames. It stands today not as a ruin, but as a fully intact, functioning building, precisely because of the revolutionary materials and methods used to create its overhead shield. The dome's construction was a breathtakingly bold act of architectural confidence. To visualize its scale, imagine a perfect sphere 150 Roman feet in diameter placed inside the building, with the interior of the dome forming the top half of that sphere. The base of this dome is 20 feet thick, a massive ring of concrete that supports the entire structure. But the Romans were brilliant weight managers. As the dome curves upward, the builders lightened the load by using a series of ingenious tricks. They created 5 concentric rings of coffers, those famous indentations in the ceiling, which aren't just decorative, they carved away tons of unnecessary weight. More critically, they changed the very recipe of the concrete itself as the dome rose higher. At the heavy, sturdy base, the concrete mix was a robust blend of pozzolana mortar and heavy, durable travertine stone aggregate. But as the builders worked their way toward the apex, they progressively lightened the mix. They swapped the heavy stone for lighter materials, eventually using porous, volcanic materials like tufa and even pumice at the very top, the lightest stones they could find. This was a masterclass in material science, tailoring the concrete's density and weight to the specific structural demands of each section. The result was a dome that was incredibly strong at its base where the stress was greatest, and progressively lighter at its crown, preventing it from collapsing under its own immense weight. Now, let's talk about the fireproofing. The entire dome is a monolithic shell of Roman concrete. There is no wooden superstructure holding it up, no hidden timber framework that could be compromised by heat. It is all concrete, from the oculus at the center all the way down to its supporting walls. This is the ultimate fireproof roof. When a fire raged through the surrounding city, embers and radiant heat would have battered the Pantheon's exterior. But the concrete shell, especially formulated with its volcanic pozzolana, would have done exactly what it was designed to do. It would have absorbed that immense thermal energy, acting as a giant heat sink. The chemical bonds within the pozzolanic mortar would have held firm, with no trapped water to turn to steam and cause explosive spalling. The fire would have found absolutely nothing to burn, because the roof itself was made of stone and ash materials already forged in fire. The Pantheon's resilience isn't a theoretical concept. It's proven by history. We know from records that fires damaged the surrounding neighborhood multiple times, including a major blaze in the year 80 of our Common Era that required extensive repairs to the building's portico. But the dome itself, the concrete core of the structure, has never needed restoration due to fire damage. It has endured through the fall of an empire, through the Middle Ages, through the Renaissance, and into the modern era, its original concrete intact. The secret to this longevity is that the Romans didn't just build a roof. They grew a stone canopy, the continuous chemical process of the pozzolanic reaction, which strengthens the concrete over decades and even centuries, means the Pantheon was actually getting stronger long after its builders were gone. It is the ultimate validation of Vitruvius's principles and a permanent, awe-inspiring monument to the Roman solution for a problem that once threatened to burn their civilization to the ground. Knowing the recipe for their incredible concrete was only half the battle for the Romans. The true mastery was in the meticulous application, a carefully choreographed process of layering and curing that transformed wet slurry into an indestructible shield. They didn't just pour a slab and hope for the best. Their technique was a symphony of precision, born from centuries of experience and a profound understanding of how their materials behaved over time. The goal was to create a monolithic, seamless barrier that was bonded directly to the underlying support, leaving no weak points for fire to exploit. This began not with the concrete itself, but with the vital foundation it would sit upon. The first step was preparing the permanent wooden framework, the centering, upon which the wet concrete would be laid. This was not a temporary structure to be removed later, as is common in modern construction. The Romans built this wooden form to be a permanent part of the roof assembly, fully encased and protected within the concrete. This was a brilliant, counterintuitive strategy. Instead of trying to eliminate what a nearly impossible task given its structural properties, they chose to completely neutralize it as a fuel source. The carpenters would construct a robust lattice of beams and planks, creating the desired curvature for a vault or the slope for a simple roof. But before a single drop of mortar was mixed, this entire wooden surface was meticulously prepared. Builders would often coat the wood with a layer of rough, porous material like broken tiles, pottery shards, or even a coarse layer of mortar. This crucial step wasn't just about creating a better bonding surface. It was about ensuring there would be no direct, intimate contact between the flammable wood and the main mass of the new concrete. This initial rough layer created a sacrificial, insulating buffer zone. With the foundation ready, the highly specialized materiarii, or concrete workers, began their craft. They didn't simply dump the mix and spread it out. The pouring was done in distinct horizontal layers, each typically around 2 feet thick. This wasn't an arbitrary choice. It was the optimal depth to ensure each lift could be properly consolidated. Workers would vigorously pack and pound the wet concrete into the forms using a variety of tools, from heavy rammers to simple hand tools. This labor-intensive process was critical. It forced the aggregate, the stones and rubble within the mix, to settle tightly together, eliminating air pockets and voids that would create structural weaknesses and, crucially, pathways for heat to travel. Each layer was given time to initial set, creating a firm enough base to support the weight of the next lift without deforming. This sequential approach allowed them to build up immense thicknesses gradually, creating the massive, thermally massive slabs that were key to their fire resistance. The choice of aggregate within each layer was also carefully considered. While the binder was always the pozzolana lime mortar, the type of stone mixed in could vary based on its position in the structure. For the bottom layers, directly above the wooden centering, they might use lighter, more insulating materials like volcanic tufa or pumice. As they built upward, they could incorporate heavier, stronger stones like travertine or brick rubble to add compressive strength. This strategic grading of materials allowed them to fine-tune the roof's properties, optimizing for both weight distribution and thermal performance. The final top layer was often a smooth, fine finish coat made with a specially selected aggregate of crushed terracotta tiles or very fine gravel, creating a durable, waterproof surface that could efficiently shed rainwater. But the Romans understood that their work wasn't done once the last layer was tamped down. The most important phase, the curing process, had just begun. Modern concrete relies on keeping its surface moist for a short period to ensure proper hydration. Roman concrete, however, required a much longer, more patient approach to achieve its legendary strength. The chemical pozzolanic reaction is not a fast one. It is a slow, steady process of mineralization that continues for months and even years. The builders knew this. They would keep the new concrete roof protected from the drying sun and wind, likely by covering it with damp straw or cloths that were regularly re-wet. This extended curing period allowed the intricate network of calcium silicate hydrate crystals to grow and interlock fully, creating a density that was impervious to both water and, most importantly, the penetration of heat. A roof cured in this way didn't just dry hard. It petrified, becoming a single, continuous piece of artificial rock that was seamlessly bonded to its protected wooden core, leaving no gap for flames to find purchase and ensuring the entire assembly would stand united against the inferno. But the Roman pursuit of the perfect roof didn't stop at just concrete and wood. Their ingenuity led them to an even more inventive solution, one that repurposed an everyday object into a cornerstone of architectural genius, the humble amphora. These were the workhorses of the Roman economy, the standard clay jars used for transporting everything from wine and olive oil to grain and fish sauce. Millions were produced, and millions were eventually broken or discarded. Instead of seeing this as mere waste, Roman builders saw an opportunity. They realized that by strategically embedding these empty, upside-down amphorae within their concrete roofs, they could solve one of the biggest challenges in large-scale construction: overwhelming weight. A massive, fireproof concrete roof is incredibly effective, but its immense mass creates enormous downward and outward thrust. This force pushes against the supporting walls, which must be built exceptionally thick and strong to resist it, limiting the span of what could be built and increasing material costs dramatically. The Romans needed a way to lighten the load without sacrificing an ounce of the roof's strength or its critical fire-resistant properties. The amphora was the perfect answer. Its elongated, curved shape was naturally strong, capable of withstanding significant pressure from above. And because it was hollow, it was mostly empty space. By placing these jars side by side within the wet concrete mix, builders could effectively carve out huge volumes of heavy material from the core of the roof slab, replacing solid, crushing stone and mortar with lightweight air pockets. The process was brilliantly simple. Workers would set the amphorae, often with their necks pointed downward, directly onto the wooden centering before the main concrete pour. They were arranged in a tight, honeycomb-like pattern, their rounded shoulders touching to create a stable, interlocked layer. Then, the concrete mixture was poured over and around them, filling the gaps between the jars and encasing them completely. The necks of the amphorae were often left open or only loosely covered with a tile, ensuring that the air trapped inside could not expand and crack the concrete when heated. Once the concrete cured, the amphorae became a permanent, integrated part of the roof structure. The result was a composite material, a thin, strong shell of fireproof pozzolanic concrete wrapped around a core of lightweight, rigid voids. This technique, a precursor to modern lightweight concrete with foam or plastic voids, offered a trifecta of benefits. First and foremost, it drastically reduced the dead weight of the roof, sometimes by as much as a third. This meant wider spaces could be spanned without needing impossibly thick walls, allowing for more grandiose and open interior architecture. Second, it enhanced the roof's fireproofing. Those trapped air pockets created exceptional thermal insulation, slowing the transfer of heat from a blazing external fire to the protected interior even more effectively than a solid slab. The ceramic amphorae themselves were already fired clay, utterly non-flammable and stable even at extreme temperatures. Finally, it was a triumph of economical and sustainable building. It turned a cheap, abundant waste product into a valuable construction material, reducing the amount of expensive pozzolana, lime, and aggregate needed for each project. We can still see evidence of this clever technique today in some of Rome's most impressive ruins. Most famously, the majestic Basilica of Maxentius and Constantine, one of the largest buildings in the Roman Forum, employed amphorae in its enormous vaulted ceilings. Archaeologists studying the fragments of collapsed vaults have found the distinct, curved shards of these jars embedded within the concrete, providing physical proof of the method. This wasn't a quirky experiment. It was a standard, refined technique used in some of the empire's most important structures. It demonstrates a level of sophisticated engineering thinking that is startlingly modern, an understanding that the true strength of a material lies not in its sheer mass, but in its intelligent application. The Romans didn't just build heavy, they built smart, using clever geometry and material science to make their structures lighter, safer, and more resilient, all with the simple, ingenious reuse of a clay jar. While the Romans were mastering the use of volcanic ash and ceramic voids, our modern approach to fireproofing has taken a drastically different path, one defined by synthetic chemistry and industrial processes. Today, we often rely on a family of materials known as intumescent coatings. These are essentially special paints or sprays applied to structural steel and wood. When exposed to high heat, they undergo a chemical reaction that causes them to swell and expand, sometimes to many times their original thickness, creating a protective, carbon-rich char that insulates the underlying material from the fire. We also use fire-resistant gypsum wallboards filled with fiberglass and other additives, and we wrap structural elements in mineral wool blankets. On the surface, these methods seem highly advanced, a product of our superior scientific knowledge. But when we place them side by side with the Roman model, a fascinating contrast emerges, not just in method, but in philosophy and long-term performance. The most striking difference is in the fundamental nature of the materials themselves. Roman fireproofing was inherently structural and monolithic. Their concrete vaults and amphora-filled roofs were the structure. The fireproofing wasn't a separate coating or an added layer. It was the very substance of the building. This created a permanent, integral defense system. Modern methods, by comparison, are often additive or reactive. An intumescent coating is a separate product applied to a structure that remains vulnerable underneath. If that coating is scratched, damaged during maintenance, or improperly applied, its effectiveness can be completely compromised. Similarly, a gypsum board can be breached by a simple hole drilled for plumbing or electrical work, creating a direct pathway for flames to reach the wooden studs behind it. Our solutions often create a fragile shield around a vulnerable core, whereas the Roman solution eliminated the core's vulnerability by transforming it into the shield. This leads directly to the second major contrast: Durability and lifespan. A Roman concrete roof, as the Pantheon proves, was designed to be effective for millennia. Its pozzolanic reaction continues to strengthen it over centuries. It is immune to water, wind, and the wear and tear of time. Modern fireproofing materials, however, can have a limited effective lifespan. Intumescent paints can degrade under UV light if exposed. Their chemical components can break down over decades, and they often require careful inspection, maintenance, and reapplication to remain certified and effective. Our solutions are frequently designed with a specific service life in mind, perhaps 50 or 100 years, after which they may need to be replaced, a concept that would have been utterly foreign to a Roman engineer, who built with the explicit goal of creating structures for the ages. Perhaps the most relevant difference for our world today is the environmental and health profile of these methods. Roman fireproofing was astonishingly sustainable by modern standards. Their key ingredient, pozzolana, was a natural volcanic material quarried from the earth. Their aggregate was often rubble from previous construction or local stone. Even their ingenious lightweighting system relied on recycled ceramic jars. The entire process was powered by manual labor and produced no toxic byproducts. Modern fireproofing, however, is deeply tied to industrial chemistry. Many intumescent coatings and fire retardants rely on complex synthetic polymers and can contain halogenated compounds or other chemicals that, when burned or even during their manufacture, can release toxic fumes into the air or leave behind hazardous waste. The production of gypsum board and mineral wool is energy intensive. Our methods excel at providing excellent fire protection in the short term, but they often come with a hidden environmental cost that the ancient material-based approach simply did not have. This isn't to say Roman technology was superior in every way. Modern science gives us incredible advantages in consistency, scalability, and understanding of fire dynamics. We can precisely engineer materials for specific thermal resistance values and test them in controlled laboratories. We can protect incredibly complex steel frameworks that allow for skyscrapers, something Roman concrete could never do. But the comparison is humbling. It reveals that our definition of advanced is often narrow, focused on immediate performance and convenience rather than longevity and harmony with natural systems. The Romans worked with the chemistry of the earth, using natural pozzolanic reactions that mimicked geological processes. We often work against it, creating entirely new synthetic compounds to solve a problem. Their legacy challenges us to consider whether the most sophisticated solution is always the one that involves the most complex chemistry, or if sometimes the true genius lies in observing the world around us and applying its timeless principles with breathtaking ingenuity. Yet for all our theorizing about Roman engineering, nothing compares to the visceral, tangible proof offered by a single catastrophic event. While the Great Fire of Rome demonstrated the terrifying need for fireproofing, a different kind of inferno, just a few decades later, would provide the ultimate, if tragic, validation of their solution. In the year 79, the volcano Mount Vesuvius erupted, burying the prosperous towns of Pompeii and Herculaneum under a deep blanket of ash and superheated gas. This was a disaster of unimaginable horror for its inhabitants, but it created a unique, frozen snapshot of Roman life. The very same volcanic fury that provided the Romans with their miracle material also perfectly preserved the evidence of how they used it, offering us an unparalleled laboratory to study the performance of their fireproof roofs under the most extreme conditions imaginable. The eruption subjected the buildings of Pompeii to a multi-stage assault far more intense than any urban fire. First came a rain of pumice stones, pounds of heavy rock falling from the sky, battering roofs and collapsing weaker structures. Then, pyroclastic surges, waves of superheated gas and ash reaching temperatures, often estimated between 300 and 500 degrees Celsius, swept through the city, instantly carbonizing any organic material in their path. Wooden furniture, food stores, and, tragically, the townspeople themselves were vaporized or turned to charcoal. This environment was a brutal test of any building material. Ordinary tile roofs would have been shattered by the initial hail of rock, exposing the wooden frameworks underneath to the incinerating gas that followed. But throughout the ruins, archaeologists have found stunning examples of the opposite. In numerous structures, particularly the more substantial homes of the wealthy and public buildings, roofs made with pozzolana-based concrete survived remarkably intact. The evidence is right there in the ruins. You can see sections of the original opus cementitium roofing, still in place after nearly 20 years. The key to their survival was their monolithic nature. Unlike a roof of loose tiles, this concrete formed a single, continuous shell. When the pumice stones struck, they might have chipped the surface, but they couldn't dislodge it in a way that created a major breach. More importantly, when the searing heat of the pyroclastic flows washed over these roofs, the concrete performed exactly as designed. The pozzolanic concrete acted as a phenomenal thermal barrier. Its density and mineral composition prevented the rapid transfer of that intense heat to the space below. While the heat on the outside was sufficient to instantly carbonize a human body, the temperature on the protected interior would have risen far more slowly, potentially allowing precious additional minutes for anyone sheltering inside. In some villas, we find carbonized wooden beams that were part of the permanent formwork, still locked in place within the concrete. This is a crucial detail. The wood wasn't burned away by flame. It was slowly carbonized by conducted heat through the concrete shield. The roof did its job. It didn't allow a direct blast of fire to consume the structure. It absorbed and resisted an overwhelming thermal attack, protecting the integrity of the building beneath it until it was finally buried and preserved by the falling ash. Perhaps the most compelling evidence comes from a fascinating contrast found in the ruins. In areas where roofs were made of traditional wood and terracotta tiles, the devastation is absolute. The tiles are found shattered on the floor beneath where the roof once was, and the carbonized remains of the wooden support beams lie amongst them, showing a complete structural failure. But just next door, a building with a concrete roof often has its walls still standing taller, with the roof itself partially intact. The volcanic materials didn't just protect the building, they protected the very evidence of their own success. The eruption of Vesuvius was a tragedy of epic proportions, but it left behind an undeniable truth. The Roman invention of fireproof concrete wasn't just a theoretical idea or a solution for common urban blazes. It was a robust, thoroughly tested technology capable of providing genuine protection even against the apocalyptic fury of a volcano, proving its worth in the most devastating laboratory on Earth. This incredible technology might sound like it was reserved for emperors and their grandest projects, but one of the most fascinating aspects of Roman fireproofing was its surprising accessibility. You didn't need to be a senator living in a palace on the Palatine Hill to benefit from these advancements. The Roman system was engineered for scale and efficiency, creating a kind of democratization of safety that trickled down through the social strata. The key to this widespread adoption wasn't just imperial decree. It was a powerful combination of smart logistics, clever material reuse, and a building industry that had standardized these life-saving methods. At the heart of this economic miracle was the sheer abundance of the core ingredient, pozzolana. The volcanic fields around the Bay of Naples were not a limited, precious resource like a gold mine. They were a vast, renewable geological deposit. The Romans established what we would now call an industrial-scale extraction and supply chain. Quarries operated continuously, and the shipment of this volcanic sand up the coast to Rome, and then throughout the empire via its superb road and river networks, became a routine commercial operation. Because the raw material was so plentiful, and the transportation infrastructure was already in place for other goods, the cost remained relatively low. It became a bulk commodity, not a luxury item. This is a crucial point. The Romans weren't shipping rare gems. They were moving dirt, and they had become masters of moving dirt cheaply and in massive quantities. For a builder in a provincial town, ordering a shipment of proper pozzolana mortar might have been a significant expense, but it was a feasible one. Much like ordering concrete today is a standard part of any construction budget. This efficiency was supercharged by the Roman talent for standardization. Vitruvius's writings did more than just preserve knowledge. They created a universal recipe book. An architect in Londinium and a foreman in Carthage were working from the same set of instructions. This meant that the process of mixing and applying fireproof concrete became a repeatable, teachable skill. Laborers, the materiarii, could train on these techniques and then take that expertise anywhere in the empire. This standardization drove down the cost of knowledge. A builder didn't need to hire an expensive, rare expert from Campania. He could hire local workers who were already familiar with the methods or who could be quickly trained. This created a competitive market for skilled labor rather than a monopoly held by a few, which further kept prices in check and made the technology more widely available. For the average Roman, the most likely point of contact with this technology wasn't a full concrete dome over their entire home, but through critical, targeted applications. A middle-class homeowner might not be able to afford a vaulted concrete ceiling for every room, but they could absolutely invest in a fireproof party wall shared with a neighbor or, most importantly, a fire-resistant roof for their most vulnerable area, the kitchen or the workshop. These were the spaces where fires most frequently started. By using a concrete vault over the kitchen hearth or a roof made with amphory concrete composite over a carpenter's workshop, a family could dramatically reduce their biggest risk. They were essentially creating fire breaks within their own homes. Archaeologists see evidence of this selective use everywhere. In the ruins of Ostia, the port city of Rome, we find modest insulae or apartment buildings where the ground floor shops have robust, fire-resistant construction while the upper floor apartments might have simpler materials. It was a pragmatic, cost-effective approach to risk management. This is where the genius of reusing amphory truly shines from an economic perspective. The Roman economy ran on these clay jars. They were the shipping containers of the ancient world, and like modern shipping containers, they were everywhere, and they were often discarded after a single use. This created a massive, continuous supply of free or very cheap lightweight aggregate. For a builder, this was a dream scenario. Instead of having to quarry, shape, and pay for expensive stone to lighten a roof, he could simply use the piles of broken pottery from the local tavern or olive oil merchant. This turned a waste disposal problem into a valuable construction resource. The cost savings were enormous, making sophisticated, weight-reducing roofing techniques accessible for a much broader range of buildings, from large warehouses and public baths to the larger homes of prosperous merchants. Ultimately, the widespread adoption of fireproof roofing wasn't just about technology or economics. It was about a cultural shift in the value placed on safety and permanence. After experiencing the trauma of city-wide fires, Romans from all walks of life began to see investment in fire-resistant features not as an extravagant luxury, but as a wise and necessary protection of their property and lives. The building codes initiated after the Great Fire of Rome under Nero and continued by later emperors created a regulatory environment that encouraged and sometimes mandated safer construction practices. This created a market demand that the private sector was all too happy to supply. The result was a remarkable achievement, an ancient society that leveraged its natural resources, its logistical prowess, and its practical engineering genius to deliver a measure of safety and resilience to its citizens, building a legacy of stone and wisdom that still shelters us today. What's truly remarkable is that this wasn't a one-size-fits-all technology imposed rigidly from Rome. The Roman Empire was a vast tapestry of diverse landscapes and geologies, and its engineers were brilliant pragmatists. They understood the core principle, the pozzolanic reaction, and then demonstrated incredible flexibility, adapting their recipe based on whatever materials were locally available. This wasn't just about convenience. It was a testament to the depth of their understanding. They knew that the magic wasn't in the specific volcanic sand of Pozzuoli, but in finding any material rich in silica and alumina that could trigger that same chemical process. So, as the legions and their engineers marched across Europe, North Africa, and the Middle East, they became geological detectives, constantly testing local soils, sands, and ashes to find workable substitutes. In the northern provinces, like Britannia and Gaul, high-quality volcanic ash was simply not an option. It didn't exist there, but the Romans found a clever alternative. They discovered that certain types of fired clay, when crushed into a fine powder, could mimic the properties of pozzolana. Specifically, they began using crushed ceramic tiles and broken pottery, a material we now call coxiopsto or testacea. They would gather this ceramic dust and mix it with the local lime mortar. The fired clay, having already been through a kiln, was rich in the reactive silica they needed. This created a hydraulic mortar that, while perhaps not quite as strong as the premier Italian pozzolana, was still exceptionally durable and water-resistant. Evidence of this is found in the remains of Roman baths and harbor works throughout Britain, where this pinkish mortar, filled with tiny brick fragments, helped structures withstand the damp northern climate for centuries. Meanwhile, in other regions, they hit the geological jackpot. The province of Africa Proconsularis, in modern-day Tunisia and Libya, had its own volcanic regions. Roman engineers there quickly identified and exploited local sources of volcanic ash that were virtually identical to the Italian variety. This meant that cities like Carthage could build to the same spectacular standards as Rome itself, with massive concrete harbors, vast bath complexes, and soaring vaulted roofs, all using homegrown materials. Similarly, in the Eastern Empire around the Aegean Sea, they found deposits of volcanic ash on the islands of Santorini and Nisyros. The famous Roman concrete structures found in Ephesus, Pergamon, and other great cities of Anatolia likely benefited from these regional sources, creating a network of construction hubs that didn't have to rely on long, expensive shipments from Italy. Perhaps the most fascinating adaptations occurred in places with truly unique geology. In the Rhine and Danube regions, for instance, where neither volcanic ash nor high-quality lime was easily at hand, They developed composite techniques. They might build a vault using local stone, but then coat it in a thick, protective layer of imported pozzolanic mortar for its waterproofing and fire-resistant qualities, using the valuable material only where it was most critical. In Egypt, they faced a different challenge, a lack of quality timber for making lime. Their ingenious solution was to use gypsum plaster, which requires much lower firing temperatures, and then combine it with local reactive materials like crushed brick to create a serviceable hydraulic mortar for less critical applications. This incredible flexibility reveals the true nature of Roman engineering prowess. It wasn't about brute force or blind repetition. It was a deeply intelligent, empirical system of knowledge transfer. A military engineer dispatched to a new province carried with him the fundamental principles outlined by Vitruvius. His first task was to survey local resources, conduct tests by mixing samples, and determine the best possible approximation of the ideal concrete he could achieve. This knowledge was then shared across the vast network of the empire, creating a living, evolving database of material science. The widespread use of these techniques, from the rainy highlands of Britain to the arid deserts of Syria, stands as a powerful testament to the effectiveness of Roman technology. It proves that their fireproof roofing and resilient concrete were not just isolated wonders of the capital city, but an adaptable, scalable system that strengthened the entire empire, allowing every province to build safer, more durable cities in their own unique landscape. This mastery, however, did not last forever. The slow unraveling of the Western Roman Empire created a perfect storm that would ultimately shatter this chain of knowledge. As centralized authority crumbled in the 4th and 5th centuries, the sophisticated trade networks that supplied pozzolana from Italy to the provinces disintegrated. The expert materiarii, the concrete workers whose skills were passed down through generations, found their specialized services were no longer in demand for grand imperial projects. Their knowledge, once so highly valued, became a dying art. Without the steady demand and the economic infrastructure to support it, the intricate process of sourcing the right materials, mixing them in precise proportions, and applying them with skilled technique began to fade from memory. The recipe wasn't lost in a single moment. It was eroded by decades of neglect, like a great road slowly being reclaimed by the forest. The final blow came with the shift in political and cultural priorities. The new Germanic kingdoms that emerged from the empire's ruins had their own architectural traditions, centered on wood. The great patron of architecture was no longer the emperor or the state, but the Christian church, which initially favored the basilica style, a design that used long, open spans perfect for congregations, but which were often roofed with massive and highly flammable timber trusses. The focus was on speed and economy to establish a presence across Europe, not on the millennia-spanning durability that had obsessed the Romans. The immense labor and cost required to produce true hydraulic concrete seemed an unnecessary extravagance in a world now preoccupied with mere survival. The deep, empirical understanding of material science gave way to a more pragmatic, immediate need to simply put a roof overhead. The result was a tragic regression in building safety that would last for nearly 1,000 years. Europe entered the Middle Ages having forgotten how to make the one material that could have protected its growing cities. The common mortar of the era returned to a simple mixture of lime, sand, and water, a material that could set hard in air but would dissolve back into mush when exposed to continuous moisture or the intense heat of a fire. Without the pozzolanic reaction, it lacked any hydraulic properties and was hopelessly weak compared to its Roman predecessor. Builders of the time had no concept of the chemical magic they were missing. They simply worked with what they had, unaware that the ruins around them held the secret to a stronger, safer way to build. This loss had devastating consequences for urban life. Medieval cities became tinderboxes. Buildings were crammed even closer together than in Roman times, with jutted upper floors almost touching across narrow, winding streets. Roofs were overwhelmingly made of thatch or wooden shingles on heavy timber frames. A single stray spark from a blacksmith's forge, a cooking fire, or a candle could, and frequently did, lead to a catastrophe that would consume entire districts. Great fires became a horrifyingly regular feature of medieval life, recorded in chronicles with grim familiarity. London suffered major fires in 987, 1135, and 1212, each one destroying large swaths of the city built from wood and roofed with straw. The vulnerability was universal, from the smallest village to the greatest cathedral city. The attempts to combat this threat were heartbreakingly primitive compared to Roman engineering. Cities organized bucket brigades and passed laws requiring households to keep a barrel of water by their door. Night watchmen patrolled the streets, calling out, "All is well," partly to reassure citizens, but also to alert everyone that a watch was being kept for the glow of a fire. Some towns eventually banned thatched roofs within the city walls, mandating they be replaced with clay tiles. But this was like treating a symptom without understanding the disease. While tiles were less flammable than thatch, they were still laid on a bed of highly combustible wooden laths and beams, replicating the same fatal flaw that had doomed Roman rooftops before the advent of concrete. A tile roof might slow a fire, but it could not stop it. This vast technological regression is starkly visible in the ruins of the era. While Roman concrete structures like the Pantheon and countless aqueducts continue to stand strong, medieval buildings required constant repair and rebuilding. The inferior mortar used in stone castles and churches often crumbled, requiring frequent repointing. Foundations were less stable, and walls were more prone to leaning and collapse without the strong, binding concrete that could unite irregular stones into a monolithic whole. The greatest minds of the age turned their attention to spiritual matters and philosophy, not to the material science of construction. The secret of the volcanic ash was not just forgotten, it was unimaginable. They walked past the enduring evidence of Roman engineering every day, seeing the thick, strong walls and indestructible roads, but they had lost the key to understanding how it was done. The knowledge didn't vanish in a single event. It seeped away, leaving behind a darker, more vulnerable world, where the shadow of fire loomed over every crowded street and every wooden roof for centuries to come. So how did this incredible knowledge, lost for so many centuries, finally find its way back into the light? The rediscovery began not with a single eureka moment, but with a slow, dawning realization among scientists and historians studying ancient ruins. For years, the endurance of Roman marine concrete was considered a kind of myth, a legend attributed to the wisdom of the ancients, or even to lost alchemical secrets. The true turning point arrived when modern materials science developed the tools to peer deep into the very heart of the material, to see its structure not as a simple mix, but at the atomic level. The primary tool for this archaeological detective work has been the scanning electron microscope. This technology allows researchers to look at a sample of ancient Roman concrete and see a landscape that is breathtakingly complex and beautifully organized. What they found was nothing like modern Portland cement concrete, which has a more homogeneous and, frankly, less interesting microstructure. Roman concrete revealed a stunning crystalline architecture. They discovered long, plate-like crystals of a mineral called strettlingite and intricate intergrowths of calcium aluminum silicate hydrate, or CaSH, crystals. These aren't just random formations. They are the key to the concrete's strength and durability. This complex, interlocking latticework creates a material that is incredibly tough, resistant to crack propagation, and able to flex slightly under stress without shattering. It's a self-reinforcing nanostructure that nature herself would be proud of. Perhaps the most exciting discovery came when scientists focused on the specific ingredients, particularly the lumps of white material often found in Roman concrete that were long dismissed as evidence of sloppy mixing or poor quality lime. Advanced X-ray microdiffraction and spectroscopy techniques revealed these white chunks to be something far more clever: pockets of undissolved quicklime. This was a bombshell finding. The modern standard is to slake lime, mix it with water fully before adding it to the mix, creating a smooth paste. The Romans, it appears, often took a more aggressive approach. They would sometimes mix the dry, highly reactive quicklime directly with the pozzolana and moist aggregate. The prevailing theory is that this created a kind of self-healing mechanism. When a tiny crack finally does form in the concrete over centuries, water inevitably seeps in. That water reacts with these leftover lime clasts, starting a new pozzolanic reaction that forms soluble calcium, which then travels into the crack and precipitates as new calcite crystals, effectively gluing the fissure shut from the inside. The Romans didn't just build structures to resist damage. They built them to actively repair themselves. This modern analysis has completely upended our understanding of the recipe. For a long time, it was assumed that Roman concrete's secret was a very low water-to-cement ratio, making it incredibly dry and dense. But the evidence of the lime clasts suggests their mixing process might have been more variable and less precise than we imagined, yet somehow more effective. The presence of aluminum from the clay in the pozzolana, incorporated into the strettlingite crystals, is now seen as another critical component, contributing to the material's thermal stability and longevity. Scientists are now actively trying to reverse engineer the entire process, not just to understand history, but to create a new generation of green concrete for our own time. By mimicking the Roman formula, we could potentially develop building materials that last for millennia, drastically reduce the massive carbon emissions from Portland cement production, and create infrastructures that are far more resilient to the elements. The irony is profound. The most advanced materials science in the world is now looking back 2,000 years for inspiration, finally decoding the silent, stony wisdom the Romans left behind in their magnificent ruins. And here's where the Roman formula reveals an advantage so profound, it could reshape our future. While the modern construction industry is one of the largest contributors to global carbon dioxide emissions, primarily due to the production of Portland cement, ancient Roman concrete operates on an entirely different environmental principle. The production of modern cement is an intensely carbon-heavy process. It requires heating limestone, which is primarily calcium carbonate, to incredibly high temperatures in massive kilns. This thermal decomposition drives off carbon dioxide, a major greenhouse gas, in two ways: from the burning of fossil fuels to heat the kiln, and as an inherent chemical byproduct of converting limestone into lime. It's a double blow to the atmosphere, making cement production alone responsible for roughly 8% of all global CO2 emissions. Roman concrete, by stark contrast, embarks on a far more environmentally harmonious path from the very moment it is mixed. The process begins with lime production, which, admittedly, also releases CO2 when limestone is heated. However, the remarkable difference unfolds over the subsequent centuries. Modern concrete, once cast, is largely inert in terms of its carbon footprint. The damage is done during its creation. Roman concrete, however, continues a long, slow chemical conversation with the atmosphere. The key lies in its primary ingredient, the lime. As the pozzolanic reaction proceeds, it doesn't just consume water, it also begins a process called carbonation. Atmospheric carbon dioxide slowly diffuses into the concrete matrix and reacts with the leftover lime and calcium-bearing phases, gradually converting them back into stable calcium carbonate, the very same mineral as the original limestone. This isn't a minor, insignificant process. Studies analyzing ancient Roman harbor structures, like the piers at Portus Cassinus in Italy, have shown that this recarbonation is extensive. Over 2 millennia, the concrete has absorbed a significant portion of the CO2 that was released during the original limestone calcination. In essence, the material is slowly pulling carbon back out of the air and locking it away permanently in a new stone. This creates a dramatically different life cycle assessment. Where modern concrete has a large, one-time carbon debt paid at the beginning, Roman concrete has a smaller initial debt that it actively works to pay down over its incredibly long lifespan. It transforms from a carbon source into a long-term carbon sink. This presents a tantalizing possibility for sustainable construction today. Researchers are now actively exploring how to adapt the Roman recipe to create modern, low-carbon concretes. By using less processed, natural pozzolans or industrial byproducts like fly ash and slag, and by optimizing the mix to encourage this carbonation process, we could develop building materials that are not just carbon neutral, but potentially carbon negative over their full life cycle. Imagine constructing a seawall or a foundation that actually cleans the air as it stands for centuries. This ancient technology, born from volcanic ash and meticulous observation, offers a path away from the environmentally costly paradigm of modern construction and toward a future where our built environment exists in a more balanced, and perhaps even restorative, relationship with our planet. While the bustling cities of Rome benefited greatly from fireproof roofs, the true strategic value of this technology was felt most acutely on the distant, dangerous frontiers of the empire. For the Roman military, fire wasn't just a domestic nuisance. It was a weapon of war and a constant threat to survival. In hostile territories, a legionary fort, or castrum, was an island of Roman order. Its security depended on maintaining its structural integrity against everything the enemy could throw at it, and that often included fire. A single flaming arrow could cripple a garrison if it landed on a vulnerable roof, making fireproofing not a luxury, but a fundamental requirement of military architecture. The design of a typical Roman fort was a masterpiece of defensive planning, and this extended to the materials used in its construction. The central buildings, the Principia headquarters, the Praetorium commander's house, and especially the Haurea granaries were absolutely critical. The loss of command structure or a season's food supply could doom an entire garrison. Archaeological excavations at forts along Hadrian's Wall in Britain and the German limes reveal that these key structures were consistently built with robust stone walls and, most importantly, fireproof concrete vaulting or tiled roofs set in pozzolanic mortar. The granaries, in particular, showcase this priority. Their floors were raised on pillars to prevent damp from spoiling the grain, and their roofs were engineered to be utterly impervious to both moisture and flame. Protecting the food supply was a logistical necessity. An army that couldn't eat was an army that couldn't hold the line. Watchtowers and signal stations, often isolated on windswept hills, relied on their fireproof roofs for a different kind of survival. These structures were the nervous system of the Roman frontier, using smoke signals by day and beacon fires by night to relay messages across vast distances. The roof of a watchtower was its operational heart. It had to be a stable, secure platform for maintaining a signal fire, but it also had to contain that fire completely. The risk of a signal fire getting out of control and burning down the very tower it was meant to protect was a constant danger. The solution was, once again, Roman concrete. By constructing the roof and the upper platform as a single, monolithic fireproof unit, often with low parapets to contain the blaze, the Romans ensured their communication network remained functional and safe. A sentry could focus on watching the horizon for enemies, not on worrying about his own tower catching fire from the beacon he tended. Beyond defense against enemy attacks, this technology was vital for the simple, everyday safety of the soldiers living in the cramped barracks. A single barrack block could house 80 men in close quarters, with their kit, cooking hearths, and oil lamps. Accidental fires were a very real and present danger. A mishap with a cooking fire or an overturned lamp in one contubernium, the 8-man room, could rapidly spread through the entire long building, costing lives, destroying vital equipment, and crippling the fort's manpower. By constructing barrack roofs with fire-resistant materials, whether with concrete clay tiles set in strong mortar, or even using the amphora method to reduce weight, the army drastically reduced this internal risk. It was a practical, force protection measure that ensured the legion remained at full strength and ready for battle. The military's adoption of this technology demonstrates a clear understanding that the greatest threats to their power were often not just the enemies outside the walls, but the vulnerabilities within. By building with fire in mind, they built fortresses that were truly resilient, allowing Rome to project its power and maintain its grip on conquered lands for centuries. Yet behind every ton of fireproof concrete and every perfectly set amphora lay a vast and often unspoken human engine that made these marvels possible. To grasp the full picture of Roman innovation, we must look beyond the materials and acknowledge the immense human effort, both forced and free, that drove this architectural revolution. The empire's ability to execute such ambitious projects on an unprecedented scale was built upon two pillars: the brutal reality of slave labor that provided the raw manpower, and the brilliant minds of highly skilled engineers and architects who provided the intellectual direction. The sheer volume of work required was staggering. Before a single batch of pozzolana mortar could be mixed, the raw materials had to be wrested from the earth. This began in the quarries and sand pits, some of the most punishing environments in the ancient world. Endless lines of enslaved laborers, often prisoners of war or those born into slavery, would toil under the sun and whip, hacking at rock faces to extract limestone. This stone was then fed into furnaces, where teams of slaves maintained the blistering temperatures needed to transform it into quicklime, a process that filled the air with choking dust and searing heat. Meanwhile, in the volcanic fields around Pozzuoli, other enslaved crews worked to dig the precious pozzolana sand, loading it by the basketful onto waiting ships. This was brute force labor, the foundational first step upon which everything else was built, and it was accomplished through a system that viewed human beings as expendable tools. The logistics of moving these materials were another monumental task dependent on forced labor, The holds of the ships that carried pozzolana up the coast to Rome were loaded and unloaded by gangs of slaves. The ox carts that transported the materials from the port of Ostia to construction sites throughout the city were driven and maintained by enslaved workers. On site, the most physically demanding jobs fell to them, hauling heavy sacks of sand and lime, crushing aggregates, carrying water, and endlessly mixing the thick, demanding concrete mortar in large troughs. This was not skilled work. It was backbreaking, repetitive, and dangerous. The scale of a project like the Pantheon's dome would have required a small army of such laborers, their collective muscle power fueling the ambition of the project's designers. Theirs was a life of anonymity, their individual contributions erased into the monolithic whole of the finished structure. Yet without their numbers and their forced exertion, the Roman building machine would have ground to a halt. But raw manpower alone could not have created a fireproof roof. The other, completely indispensable side of this equation was the small class of highly trained, experienced experts, the architects and engineers. These were often freeborn citizens, sometimes even of high social standing like Vitruvius, who possessed a deep education in mathematics, geometry, and physics. They were the masterminds. The architect or architectus was responsible for the overall vision, creating the detailed plans, calculating proportions, and ensuring the aesthetic and functional harmony of the building. He determined the precise curvature of a vault, the thickness of a wall, and the complex grading of aggregates within the concrete to manage structural stress. Working alongside him was the practical engineer, the man who could translate those drawings into reality. He understood the properties of materials, the behavior of mortar, and the intricacies of formwork. He directed the specialized teams of skilled freedmen and artisans, the materiarii concrete workers, the chementarii masonry experts, and the carpenters who built the complex wooden forms. These were not slaves. They were trained professionals who took pride in their craft. The engineer had to solve real-world problems on the fly: how to support the immense weight of wet concrete during construction, how to ensure it cured evenly without cracking, and how to orchestrate the entire chaotic symphony of the construction site. The intellectual spark of the architect and the practical genius of the engineer were meaningless without the thousands of hands to execute their vision. And conversely, all the muscle in the world was useless without the guiding intelligence to direct it. This created a stark and profound dichotomy at the heart of Roman achievement. The soaring intellectual ambition that could conceptualize a dome that would last millennia coexisted with a brutal economic system that relied on human bondage. The elegant geometry and precise material science existed only because a vast underclass was compelled to perform the exhausting, often deadly, work of bringing it to life. We can stand in awe of the Pantheon's perfect proportions while also acknowledging that its grandeur was purchased with immense human suffering. This isn't to diminish the genius of Roman engineering, but to understand its full, complex cost. Their legacy is a dual one, a gift of architectural wisdom that still inspires us today, and a sobering lesson in the human price that can be paid for monumental progress. For the Romans, a fireproof roof was far more than a clever engineering solution. It was a profound statement of identity, power, and divine blessing. In a world where the gods were believed to directly intervene in human affairs, a building that could stand defiant against a force as primal and destructive as fire was seen as nothing short of a miracle. This wasn't just about practical safety. It was about crafting a visible, tangible symbol of Rome's unique place in the cosmos. a declaration that their civilization was protected by powers greater than any mortal flame. This symbolism was most potent in their temples. The house of a god demanded permanence. A wooden roof over the statue of Jupiter Optimus Maximus would have been unthinkable, a sign of doubt in the very deity it was meant to honor. By constructing temples with soaring, fireproof concrete vaults, the Romans were making a theological statement. They were building a literal heaven on earth, a permanent, imperishable home for their divine protectors. The immense, unburnable canopy overhead represented the stability and eternal order the gods provided. It sent a powerful message to every citizen and visitor. The gods reside here, and their power shields this place from chaos and ruin. A fire might sweep through the city and consume the homes of men, but the dwelling places of the gods would remain untouched, their authority and the state's connection to them unbroken. This created a psychological anchor for the populace. Even in the aftermath of a terrible disaster, the temples would still be standing, a sure sign that the favor of the gods had not been completely withdrawn, and that the foundation of the state itself remained solid. This architectural invincibility was also a crucial tool of political propaganda and a demonstration of Roman superiority over conquered peoples. Imagine a chieftain from Gaul or a diplomat from a Hellenistic kingdom visiting Rome for the first time. They would be led through the bustling forum, surrounded by breathtaking marble facades, but the most subtle and impressive feat might be explained to them, that these vast buildings were capped with roofs that could not burn. For cultures that lived in constant fear of the devastating village fire, this would have seemed like a form of magic, a technology so advanced it bordered on the divine. It was a silent, overwhelming display of Roman ingenuity and control over nature itself. The message was clear: a people who can tame fire can tame the world. This visible evidence of superiority helped to justify Roman rule. It presented Rome not as a brutal conqueror, but as a civilizing force, bringing not just laws and roads, but safety and divine order to what they considered barbaric lands. The fireproof roof became a metaphor for the unshakable, protective strength of the empire itself. The cultural importance extended deeply into the Roman concept of pietas, a complex idea encompassing duty, loyalty, and respect for the gods, the state, and one's ancestors. Using the most advanced, durable materials for public buildings and temples was an act of pietas. It was a demonstration of the community's commitment to honoring its obligations to the gods and to preserving the legacy of past generations for those to come. Building in wood or other perishable materials could be seen as short-sighted or even disrespectful, a failure in one's duty to ensure the permanence of the state and its traditions. A fireproof vault was a promise carved in stone and mortar, a promise that the achievements, the memories, and the sacred spaces of the current age would be safeguarded for the future. This wasn't just engineering. It was a moral and cultural imperative, a physical manifestation of the Roman vow to uphold civilization against the ever-present threats of chaos and oblivion. The roof overhead was a guardian of memory, ensuring that the glory of Rome would not be so easily erased by a random spark. But to truly grasp the miraculous nature of this ancient concrete, we need to peer into its very heart, into a hidden crystalline world that the Romans themselves never saw, yet somehow engineered with breathtaking precision. Modern scientists, using tools like electron microscopes and X-ray diffraction, have unlocked the final secret of this 2,000-year-old material, and it revolves around a remarkable mineral called aluminum tobermorite. This isn't just a component of the concrete. It's the very source of its supernatural strength and its incredible resilience to heat, The process begins the moment the pozzolana, lime, and water are mixed. A slow, silent chemical symphony starts, one that doesn't stop after a few weeks of curing, but continues for centuries. The initial reaction forms a common binding gel, but as the concrete ages, something extraordinary happens. Tiny, plate-like crystals of aluminum tobermorite begin to nucleate and grow within the matrix. This mineral is incredibly rare in nature, but it thrives within the carefully engineered environment of Roman concrete, forming a dense, interlocking network that reinforces the entire structure. The presence of aluminum, leached from the clay minerals in the volcanic ash, is the critical ingredient that allows tobermorite to form and remain stable. These crystals are not static, they are dynamic. When the concrete is exposed to moisture over time, a process that would normally weaken modern concrete, it actually percolates through the material and reacts with the leftover lime clasts, fueling the continuous formation of more aluminum tobermorite crystals. This is the secret to the self-healing property researchers have observed. When a tiny micro-crack forms, water seeps in and interacts with the uncooked lime, triggering a new pozzolanic reaction that fills the fissure with fresh, strong crystals, effectively gluing the crack shut from the inside out. The material doesn't just resist damage. It actively repairs itself, growing stronger with age in a way that defies all modern engineering principles. Now, apply this knowledge to a fire. When a Roman concrete roof is subjected to intense, blistering heat, this crystalline network doesn't fail. It undergoes a fascinating transformation. The heat acts like an accelerant for the pozzolanic reaction that has been slowly ongoing for centuries. It essentially gives the chemical process a massive burst of energy. The aluminum tobermorite crystals, already stable at high temperatures, can actually reconfigure and multiply under the thermal stress. The heat drives out any remaining free water that hasn't been chemically bound, further densifying the material. Meanwhile, the complex, interlocked structure of these crystals prevents the kind of explosive spalling seen in modern concrete. There are no large pockets of water to turn into steam and blow the roof apart. Instead, the heat is absorbed by the immense thermal mass of the concrete and dissipated through its complex mineral lattice. The roof essentially gets a heat treatment, emerging from the inferno not weakened, but in some ways even more strengthened and consolidated. This is the ultimate irony of Roman engineering. They created a material that was not only fireproof, but was actually tempered and improved by the very thing it was designed to resist. Their volcanic rock, born in fire, was only perfected by it. So how do we move from admiring these ancient ruins to truly understanding the hands that built them? For modern scientists and historians, the answer lies in a fascinating, hands-on endeavor, the attempt to reverse engineer and physically recreate authentic Roman concrete. This isn't just an academic exercise. It's a practical challenge that forces us to confront the gaps between their empirical knowledge and our own scientific understanding. The goal is to mix a batch of mortar that doesn't just look right, but that performs with the same legendary strength and durability, and in doing so, we uncover the profound artistry hidden within their seemingly simple recipe. The first major hurdle is sourcing the right ingredients with the same mineralogical purity the Romans took for granted. A modern researcher can't simply order a bag of Roman pozzolana from a supplier. They must travel to the original sources around the Bay of Naples, to the very quarries the Romans used, and collect samples themselves. But even then, the challenge is immense. Volcanic ash isn't a uniform product. Its chemical composition can vary dramatically from one stratum to the next, Even within the same cliff face, the Romans, through centuries of trial and error, knew exactly which seams to mine for the most reactive, silica-rich ash. Modern teams must conduct extensive X-ray fluorescence and diffraction analysis on dozens of samples just to find a match for the ancient material, a process the Roman materiarius would have judged by color, texture, and perhaps even taste. Then comes the lime, which presents its own complex puzzle. As we've learned, the Romans sometimes used a hot mix method, incorporating lumps of unslaked quicklime directly into the moist mortar. Recreating this is as much about technique as it is about chemistry. Researchers must carefully crush pure limestone and fire it in a kiln at the exact temperatures the Romans would have used, around 900 degrees Celsius, to produce reactive quicklime. Handling this material is dangerous. It reacts violently with water and can cause severe chemical burns, which speaks to the incredible skill and courage of the Roman workers who manage this process routinely. The modern experimenter must then decide on the proportions: how much quicklime to leave whole, how much to pre-slake into a paste, and how to combine it all with the pozzolana and aggregate. Vitruvius gives ratios, but he doesn't provide a detailed, step-by-step manual for every possible mix. The actual mixing process is a physical ordeal that reveals the sheer brute force required. Roman concrete was not a pourable slurry like its modern counterpart. It was a thick, sticky, dry mix with very low water content. To replicate it, researchers use heavy wooden troughs and imitate the ancient methods of manual mixing with shovels and hose. It's backbreaking work to achieve the uniform consistency needed, a task that would have been performed for hours on end by teams of laborers on a Roman construction site. This hands-on experience quickly shatters any modern arrogance. It becomes clear that achieving the right feel for the mortar was a critical skill passed down from experienced workers to apprentices, a nuance completely lost in written texts. Perhaps the greatest lesson from these experiments is the need for patience, a virtue in short supply in our modern world of rapid results. After the concrete is placed into wooden forms, the real test begins: the waiting. Modern Portland cement concrete achieves most of its strength within 28 days. Roman concrete, with its slow pozzolanic reaction, is just beginning its journey. Researchers who have cast samples find that they must monitor them for months and even years, tracking the gradual development of strength and the formation of those key minerals like aluminum tobermorite. They simulate real-world conditions, submerging samples in seawater to replicate harbor conditions, or subjecting them to cycles of heating and cooling to test fire resistance. The results are humbling. The modern samples do become stronger over time, but they have yet to match the exact nanostructure and resilience of 200-year-old concrete. This suggests that the Roman process benefited from a factor we can scarcely replicate: time itself. Their structures gained strength over centuries, a timescale impossible for any laboratory experiment, reminding us that some secrets of the ancient world can only be unlocked by the relentless passage of the ages they were built to withstand. A fireproof roof, as brilliant as it was, could not stand alone against the chaos of a densely packed ancient city. The Romans understood this with a clarity born from bitter experience. They recognized that a single ingenious technology was merely one piece of a much larger defensive puzzle. Their true mastery lay in their holistic vision, integrating fireproof roofing into a comprehensive, city-wide system of fire prevention that combined architecture, infrastructure, and human organization in a way the world had never seen before. This was not a series of isolated solutions, but a deeply interconnected strategy where each element supported and amplified the others, creating a resilient urban ecosystem designed to stifle disaster before it could breathe. The first and most crucial layer of this strategy was creating physical barriers to the fire's spread, and this is where fireproof roofing found its most powerful partner, urban planning. In the smoldering aftermath of the Great Fire, new building regulations, often attributed to Nero but expanded by later emperors, fundamentally reshaped the Roman cityscape. They mandated wider streets and broader thoroughfares. This was a deliberate engineering calculation. A narrow alleyway acts like a chimney, funneling heat and embers from one wooden eaves to another, allowing a fire to leap across the gap with ease. But a wide street creates a firebreak, a gap of clear air too vast for most airborne embers to cross. The heat radiating from a blazing building on one side would be insufficient to spontaneously ignite the structure opposite. This simple spatial rule forced fires to remain more localized, containing the damage and giving the next element of the system, the responders, a fighting chance. But even the widest street is useless if the fighters have nothing to fight with. Here, the Romans deployed their second monumental advantage, the aqueduct. These soaring arched conduits were the cardiovascular system of the city, pumping a continuous, massive supply of fresh water into the urban heart. Public fountains, baths, and cisterns were not just amenities. They were a distributed, high-capacity water grid. In the event of a fire, this infrastructure became a life-saving network. Bucket brigades could form a human chain from the nearest fountain or cistern directly to the blaze, providing a constant, if rudimentary, flow of water. More importantly, the abundant water supply enabled the operation of the sipho, a primitive but effective piston-powered water pump that could project a stream of water a surprising distance. This technology, combined with the strategic water access points, meant that responders weren't just throwing dust on an inferno. They could actually attack it with targeted force, something impossible in cities that relied on wells and stored rainwater. This brings us to the human element, the organized force that would wield these tools, the Vigiles Urbani, the watch of the city. Established by Emperor Augustus in the wake of yet another devastating fire, the Vigiles were the world's first full-time, professional public firefighting and police force. This was a revolutionary concept, comprising 7 cohorts of roughly 1,000 freedmen each. They were stationed in barracks spread strategically across the city's 14 districts. Their training was constant. They were equipped with buckets, axes, hooks for pulling down burning buildings to create fire breaks, and most crucially, those siphons. But their role began long before the first alarm was raised. They conducted nightly patrols, watching for the telltale glow of an unattended hearth or a stray spark, enforcing the new fire prevention codes, and ensuring that homeowners kept a supply of water in their courtyards as a first line of defense. They were the nervous system of the entire fire prevention strategy, the active, intelligent force that connected the passive resilience of the architecture to the powerful flow of the infrastructure. And this is where the fireproof roof completes the system. Think of a city without them. Even with wide streets, a fire starting in one district would launch a storm of burning embers high into the air. These glowing projectiles would sail over the fire breaks, landing on the vulnerable wooden roofs of buildings blocks away, igniting secondary blazes that would quickly overwhelm the Vigiles, no matter how fast they ran or how much water they pumped. The fireproof roof changed this equation entirely. A roof made of pozzolanic concrete or sealed tiles was an impassable barrier to these airborne embers. It turned entire city blocks into fire-resistant zones, effectively containing the fire's ability to jump. This allowed the vigiles to focus their efforts on the original blaze and its immediate vicinity, rather than being stretched thin chasing a dozen new outbreaks across the city. The roof was the stalwart guardian that held the line, giving the urban planners' fire breaks their teeth and the firefighters the precious time they needed to do their jobs. It was the final, critical piece of a magnificent defensive triad. The urban plan contained the fire's path, the aqueducts supplied the means to fight it, and the fireproof roofs denies the fire the fuel it needed to escape. Together, they transformed Rome from a tinderbox into a fortress, a testament to a systematic approach to public safety that would not be seen again for over 1,000 years. This ancient wisdom, locked away for centuries in the ruins of the empire, is now experiencing a remarkable renaissance on the drawing boards of 21st century architects and engineers. Far from being a forgotten relic, the Roman approach to fireproofing is providing a powerful blueprint for tackling two of the most pressing challenges in modern construction: improving fire safety and radically reducing the environmental footprint of our buildings. Today's innovators aren't just looking at history with nostalgia. They are actively deconstructing the Roman recipe, using advanced scientific tools to understand its secrets, and then re-engineering those principles for the demands of our own era. This isn't about imitation. It's about translation, taking the core logic of a 2,000-year-old technology and giving it a new voice in concrete and steel. One of the most direct lines of inheritance is the renewed interest in the very material that made it all possible: volcanic ash. The modern production of Portland cement is an environmental nightmare, responsible for a significant portion of global carbon dioxide emissions due to the immense energy required to heat limestone kilns. In response, a growing movement within the construction industry is pushing for the use of supplementary cementitious materials, or SCMS, to replace a large portion of that carbon-intensive cement. And the most effective SCMS available are natural pozzolans, the exact same type of volcanic ash the Romans quarried. Companies are now actively mining deposits in places like California, Germany, and Indonesia to produce modern pozzolan blended cements. When mixed, these blends undergo the same pozzolanic reaction Vitruvius described, creating a concrete that is not only stronger and more durable, but also possesses superior fire resistance. By replacing up to 40% of the Portland cement with this volcanic powder, we can drastically cut CO2 emissions while simultaneously creating structures that are inherently more resilient to extreme heat, making the ancient solution a cornerstone of modern green building standards. The inspiration extends beyond just the ingredients to the very structure of the material itself, echoing the Roman use of amphory, the principle of lightweighting, reducing a structure's dead weight to allow for larger spans and less massive supports, is more relevant than ever as we build taller and more ambitious skyscrapers. While we don't use broken clay jars anymore, the fundamental idea is alive and well in the form of modern void-forming systems. Construction teams now regularly use large, lightweight plastic spheres or hollow foam blocks that are placed within concrete floor slabs and roofs. Once the concrete is poured and sets, these voids become permanent, dramatically reducing weight without compromising structural integrity. Just like the Roman amphory, these voids also create trapped air pockets that provide exceptional thermal and acoustic insulation. This modern interpretation of an ancient technique demonstrates how the Roman philosophy of intelligent, material-efficient design is directly influencing how we build more sustainable and efficient structures today. Perhaps the most cutting-edge field of research involves the pursuit of the ultimate Roman marvel, self-healing concrete. The discovery that Roman concrete contains pockets of quicklime that can react with water to seal micro cracks has ignited a global race to develop a modern equivalent. Scientists and companies are experimenting with a host of innovative solutions. Some are embedding concrete with tiny capsules containing healing agents like silica gel or bacteria that are activated when water enters a crack. Others are developing polymer-based fibers that can melt under heat from a fire and flow into fissures. The goal is the same one the Romans achieved seemingly by accident: to create a living material that can maintain itself, reducing the need for costly repairs and dramatically extending the lifespan of our infrastructure. This research, funded by government agencies and private industry alike, stands as the ultimate tribute to Roman engineering, a concerted, global effort to reclaim a lost technology that they perfected through observation and sheer brilliant intuition. This legacy is no longer confined to research labs. It is already taking physical shape in pioneering structures around the world. Architects committed to sustainability are specifically designing buildings that utilize pozzolana-based concretes for their superior environmental and fire-resistant properties. The Palazzetto dello Sport, built for the 1960 Rome Olympics, used a lightweight concrete inspired by ancient techniques for its iconic dome. More recently, the construction of the massive naval base at Port of San Diego in the United States utilized a Roman-inspired concrete mix for its submarine breakwater, designed to last 120 years in the harsh seawater environment. These projects prove that the Roman approach is not a historical curiosity, but a viable, powerful, and commercially successful building strategy for the modern world, merging unparalleled durability with environmental responsibility in a way that few modern materials can match. So as we reflect on the journey of Roman fireproof roofing, from the ashes of the Great Fire to the soaring dome of the Pantheon, we're left with a humbling realization. This wasn't just a clever ancient hack. It was a sophisticated, holistic system of material science, logistics, and urban planning that, in many ways, surpassed our own modern approaches. Their concrete doesn't just resist fire. It becomes stronger over centuries, actively repairs its own cracks, and even cleans the air by reabsorbing carbon dioxide. Compare that to our modern fireproofing, which often relies on synthetic coatings that degrade over time, require constant maintenance, and can release toxic chemicals. The Romans built for eternity with natural, earth-born materials, while we often construct with complex chemicals designed for decades. Their achievement stands as a powerful testament to a different kind of wisdom, one that sought harmony with the natural world rather than dominance over it through industrial force. This legacy stretches far beyond just roofs. It challenges our very definition of progress. We live in an age of breathtaking technological acceleration, with microchips and smart materials the Romans could never have dreamed of. Yet, their concrete has outlasted empires and continues to teach us profound lessons in durability and sustainability that we are only now, with our electron microscopes and advanced chemistry, beginning to fully decipher. It forces us to ask a deeply compelling question. If they could achieve so much with observation, intuition, and the materials beneath their feet, what other forgotten secrets might still lie buried in the dust of history? What other ancient technologies, dismissed as primitive, might hold the keys to solving some of our most pressing modern problems? The Romans have handed us a powerful blueprint, not just for building stronger structures, but for thinking differently about our relationship with the planet and the timeless ingenuity of the human mind. Their silent, stony wisdom endures, waiting for us to listen,